All right. So the next speaker is Martin Vechev from ETH. So this is the 6th time that I introduce Martin for this occasion. And every time when I take some notes to prepare and write down his research area, there's at least one more bullet to add and at least 10 more PLDI papers to consider. So the research includes concurrency, static analysis, dynamic analysis, deep code, probabilistic programming, safe and interpretable AI, software-defined networks, and several more. Today he's going to talk about deep learning and how to make that safe. So go ahead.
All right, thanks. Yeah. All right, so I want to talk a little bit about like some of the topics that we're working on. So I'll pop up a little bit on and give you a bit of perspective. And it requires a little bit of context here to tell you about kind of the focus of what we've been doing over the last few years. So roughly, it sits a lot of the projects that we're looking in the last few years sit like at the intersection of symbolic methods, symbolic techniques, and probabilistic reasoning, machine learning, data-driven methods, right? And so in symbolic techniques, and that's sometimes referred to as like the first wave of artificial intelligence, right? But this first wave is still going very strong. It has not ended yet, and still going. So they're very strong in like logic, deduction, abstraction, modularity, and all the things that exist there are type inference, abstract interpretation, all these things we know, formal methods. And then on the other side, on your right, is a lot of these methods like probabilistic reasoning, machine learning, optimizations. They're good with dealing with noise. They're good with dealing with uncertainty, right? So the idea here in a lot of these works that we've been looking at is to try and combine the strengths of both of these techniques and both of these directions, let's say. And sometimes it's referred to as the third wave of AI. Nobody knows exactly what that means, but it is something that combines symbolic reasoning and probabilistic reasoning. So you can think of it as systems being able to explain their decisions, for instance. But combining this kind of like paradigms, which are like quite different. Like you have like continuous reasoning here, gradient-based reasoning. Here you have like deductive reasoning and so on. So they're really far apart and trying to bridge them. So over the last few years, we've been working on a bunch of directions in this intersection. And before I go into the deep learning, I wanted to give you like a little bit of an overview because it may be interesting to some of you, some of the other directions. So one of the directions we've been looking at is this direction of probabilistic programming, where we build like our own solver for exact inference in probabilistic programs. So that's publicly available. And one of the uses of this solver, it's kind of like an SMT solver for probabilistic programming, is that you can compile problems in security, networking, and some of the things Peter mentioned down as programs in this language of C. Another thing we've looked at for a while is this, you're still looking at, is this area now has become of learning from large databases of code. So things like GitHub, for instance, and learning probabilistic models and solving problems there. So there is like an ETH spin-off here called Deep Code, which is some of the people are here in the audience, which has moved on to solving, I'd say, like really large-scale static analysis problems at really large scale with custom solutions and custom machine learning and so on. So go check it out, like at this link there. Now, some of the more recent direction we've been looking at this intersection of like symbolic and symbolic reasoning and probabilistic modeling is one of these here, like which we refer to as like machine learning guided solvers. So this is how do you use probabilistic reasoning, machine learning to actually speed up engines that we use often, like analysis, SMT solvers, SAT solvers, and other engines like this. So you can go over here on this website and find one of the latest one we've built. It's a way to use reinforcement learning, imitation learning to speed up SMT solvers by an order of magnitude without actually changing the solver. So that's actually a NIPS paper, an oral NIPS paper coming up soon, and the code will be public also. Now, what I actually want to talk about today is one of the remaining 4 directions here on trusted artificial intelligence and some of the open problems that we are facing with making deep learning more reliable and secure, more interpretable, more explainable, more transparent, more accountable if you want. So we actually have a course here, a graduate course here that we're teaching at ETH. There's more than 200 students in this course from robotics, machine learning, programming languages, all kinds of areas where we're looking at some of the latest research that people are doing and we're doing and others. So let's look at this a bit, and I will tell you a little bit more technically about like 2 of these directions here and tell you about what the problems are. So I will not spend so much time like telling you about the concrete, specific technical things we do, but tell you about the problems that people are facing. Now, one thing I'm glad about this direction is that actually I can show pictures here. Normally it's a bit hard. Huh? Pictures are fun. Yeah, it's good. So some of these pictures you may have probably seen before, and they illustrate that deep learning systems today are somewhat unstable to perturbations. They tend to be a little bit non-robust, let's say. So if you have a picture of an animal here like panda and you add a bit of noise, the machine learning system, the deep learning network can classify it as a gibbon with a pretty high confidence of 99%, even though to a human it would actually, a human would have no problem classifying it as a panda. And there are many such attacks that people have performed on deep learning systems, and they keep performing, and more of these works are coming out, okay? Now, so this kind of illustrates that's like one of the motivations, but there are many others, like decision making and causality and so on, illustrates that potentially there is an interesting opportunity to look at these intersections of logic and symbolic reasoning to making deep learning more reliable, more safe, more interpretable. Okay? So here are the 2 directions that we are looking at, and I'll talk about both of them, starting with this one first on the right, and then go into this one here, the certification of deep learning, and tell you about some of the open problems there. So this first direction here on DL2, combining deep learning with logic, is motivated by the fact that you would like to have an easier way to interact and to work with deep learning neural nets. Okay? So let me give you an example what you may want to do and what the system that we built can do. So here you have a neural network on the left, and here you have a picture of a deer, but you probably cannot see it. Okay, so it's actually a picture of a deer. Trust me, it's a picture of a deer. And we have built this engine here in the middle in blue, where it can actually take a query like this. So you can actually ask questions, and you can interact with the neural net and ask it for various questions that you may be interested in. So for instance, adversarial examples, the ones that I showed you on the previous slide, can actually now be encoded as just a query. So you can ask something like, find an image where the image is in some range, the pixels are in some range, such that the image gets classified to 9. That's a truck, for those who are wondering. 9 is a truck in this data set, such that the image that you find is close to this input image that you gave here. All right, so I can ask a query like this. So one thing you see here is that you start introducing logical constraints here. I give you an input to the neural net, and I want to find a similar input that gets classified differently. So that's like a simple example here. I need to output you some image that looks the same as the other one, but now it's classified as a truck. Okay? Here is another example. You may wonder, for instance, a common thing in deep learning is training multiple networks on the same data set. Maybe you have a quantized network, finite precision, arithmetic or something, and you have a bigger network, and you wonder what the differences are. So here are 2 networks, and here is an image again. And so what you can ask here is find the separating image, which gets classified differently by the 2 networks. Okay? Now, the queries I'm showing you here, if you start looking at the literature, some of them would actually end up entire papers. So people can write papers about one of the query. In fact, this was a paper in SOSP last year. So you can encode queries like this and ask the neural network for questions. Another thing you may want to do is to actually enforce logical constraints on the network. So you might want to train the neural network in a way that it satisfies the property. So you have network topology, you have a data set, you can give a logical property, and then somehow train it to satisfy this property. Because you may want to convey some knowledge that you have about the world. So how do you do this? I will not talk in detail how exactly this happens, but there is a kind of a key method here that happens, that you have to bridge the logic with the differentiable training that takes place here. And that's if you take a property that you wonder about, you may want to query about it or enforce it. So here we have some octagonal property. I'm just giving you an example here. And that octagonal property here has some satisfying assignments for the variable x and y. And I have visualized it here. So one thing you can do is you can actually take this octagonal property, these logical constraints, translate them to a logical loss, and that mathematical loss here would have surface at 0 that looks very similar to this. In fact, it's the same. And once you translate it to a loss, the logic to a loss, you can train with that loss, or you can query with that loss, and solve for this using standard gradient-based methods. First-order methods, second-order methods, doesn't matter. And so that's the key idea here. You go from logic to loss, and then you reuse all of the machinery that you have already in TensorFlow, PyTorch, or whatever deep learning system you're using. So that's the key idea. Now let me shift a little bit to the other direction. So this work I just showed you, I actually haven't talked about it so far. That's in submission. So now let's get back to these examples and tell you about the other direction we're looking at. So in this direction here, what we're interested in is to actually take a network and be able to actually certify the network and show that certain property hold about the network. Okay, I don't want these surprises that there are adversarial attacks. I may want to show, for instance, that there are no adversarial attacks and prove this once and for all. So how would you do this? And there are various works on this going on in machine learning, in security, less in programming languages, I'd say, but recently also in programming languages, which are exploring different methods of solving this problem. So here's the two-step approach, okay? So in the first step, what you're going to do, and I'm going to illustrate it on the attackers. Same thing holds for arbitrary properties, but let's look at the attacker. It's a bit more concrete. So what you're going to do, you're going to take your image, the one that you want to attack the network with, the one you want to perturb, and you want to like go from a deer to a truck by changing a few pixels. And what you're going to do, you're going to define a formal spec. And the way that you define a formal spec is essentially by putting a region around the image. So what you're saying is the attacker is allowed to perturb the image in all these possible ways. One common way to define this region, the attacker region or the adversarial region if you like, is to take the image and to put a bow around it. And what that means is it essentially considers all of the possible images that are within some distance to that image that you want to attack. And there are different norms, different distances. In this case, we've used the L infinity norm. That's one that has been accepted as being a good proxy for visual similarity, let's say. So here I have taken image 8, and I have built like a big cube that captures all of the possible images that are close to X within some distance, epsilon. Once you do this, you essentially end up with a symbolic formula here. If you like, you can think of it as having a box interval around every pixel in the image, not a single point. And what the attacker tries to do, the job of the attacker, is to go around here and to go around this cube and try to find one of these points which it can give to the network, and the network misclassifies it. To not be 8, to be something else. Does this make sense, this prompt statement? All right. In the second, so once you do this, step 1, I take the 8, put a region around it, epsilon distance or a bigger distance, whatever norm I want to use. This defines a formula here, so I have 784 pixels. Before I had concrete values, now I have ranges instead of concrete values. Right? So this is a symbolic shape, and the second step that you do once you define the specification is that you propagate that specification, the entire region, through the network using symbolic techniques. And once you propagate it through the network, you're going to end up at the end with some shape here. So normally you propagate the point. Normally you take an image and you just propagate it, or you take another image and you propagate it. But there is a potentially infinite number of images here, or a very, very large number. You propagate the symbolic shape, you get another symbolic shape at the end, and what that thing here is, it essentially captures all the possible probability distributions on the labels. Again, potentially an infinite number. So that's as technical as we are going to get here. How do you propagate symbolic information for the network? This is generally a loop-free program. And the way that we do this here is by using abstract interpretation, and specifically numerical abstract interpretation. All right? So, what are the challenges here? And what you'll find here is that these arrows here, which are the abstract transformer, which take a symbolic image and transform it by going through the network layers, layer 1, layer 2, layer 3, layer so on. You know, there are many different ways to define these domains. There are many different shapes that you can use, different trade-offs between scalability and precision and performance. All right? So, you can do that. We've done this over the last year or so, 2 years. So initially there was a work on in Oakland SNNP, which defined a generic framework how to do this with abstract interpretation. Now this is been subsumed in a sense. And what we did later was we picked up a specific abstract domain that defines those shapes with custom transformers. That's about to appear at NIPS this year. And now in Popo, we have a new work which is about defining a restricted polyhedra domain, which is more precise than the zonotopes, and which is even more tailored to neural networks and gives you better precision than this one. So the lower you go, the lower you go here, the more precise you get, and the less scalable you get. The less scalable you get, the smaller networks you can handle. The more precise you get, well, the less scalable you are. Finally, in this work that's currently under submission, we're showing how to combine abstract interpretation techniques with mixed integer linear solvers in order to get even more precision. Okay, so that's the first work that shows you how to actually combine both of these techniques together. So we have a bit of experience with this problem of analyzing neural nets. One other thing you can do with this, so somebody can say, well, you take the network, you analyze it, you prove something, okay. But the experience shows that if you just, it's like taking a program that has bugs, and you're saying, I find bugs. Okay, yes. What if you can train the neural network so that it is already more defendable against these attacks? So what it turns out is that you can actually use these techniques, all of these techniques, to actually use abstract interpretation to actually train your network. So you can do your forward pass as I just described, and then put the result as part of the loss, and then try to optimize for that. So this is a paper we had in ICML this year, which shows you how to actually use abstract interpretation to train the network to be more robust. All right. And what you see in this table is that this is, I believe, on MNIST data set, and it's a convolutional network, 124,000 neurons with an L infinity bow epsilon 0.1. One thing that you see here is that this is the baseline, or I train it without any defenses, nothing, I get pretty high accuracy here, but the probability against the attack is very low, so you can attack this network relatively easily. There is a state-of-the-art defense by Madri called the PGD defense. This one also trains the network in a way which has high accuracy, but it is still not that provable here. If you use this method that I showed you, differentiable abstract interpretation, you can get still good accuracy, but be a lot more provable. So it's harder to find attacks there. So if somebody comes and says, I'm finding attacks on neural nets, well, are you finding it on trained neural net to be defended, on untrained networks? So how are you actually doing it? Now, the fundamental idea here is that in order to do this, you have to actually be able to do automatic differentiation on your abstract transformers. But you leverage this from the underlying frameworks like PyTorch and TensorFlow. Okay, so I think that this work is important in kind of bridging abstract interpretation. How do you apply it actually during training? And there's a lot more work to be done here.
Quick question.
Yeah. This one?
No, the table, right?
Yeah.
So for the certified percentage, how did you calculate the percentage?
Which one? This one?
Yeah,
You look at the test data set and you can just see.
How many of them?
Yes.
Okay.
Yes. No more questions. So one thing I want to do now, and that's why I did not talk about the propagation of the symbolic element for the network, because that would take us another hour to go for like the mathematics of how you compute zonotopes, is to actually tell you about what I see as some of the interesting problems going forward here in this space. So the first thing you have to worry about, and people are not yet, I think, worrying about enough here, is that what is the specification that you're actually proving about the network? Well, we take an image and you put a region around it and you prove that, okay, that's fine. There are different ways to define this region. But what about richer changes? Like, what about geometric perturbations? Why are all of the points inside the region equally likely somehow? Some are more important, some are less important. So I'm not yet dealing with distributions in any way at the input. Another weakness in a lot of the works is the fact that they're dealing with a bounded set of images or a bounded set of points. So they don't make guarantee about all of the possible images, all of the possible inputs that the network can take. So how do you address these problems here? So this situation here about the spec is very important, because when you're doing abstractions, it's always done with respect to a specification. You cannot do abstraction without knowing what the spec is, because you don't know what to forget. So they're somehow intertwined. Now in the verification itself, in the analysis, if you like, the question of what is a good abstraction to propagate information through the network, well, there were a few that we came up with, but I'm sure there are many more. Many different ideas that people can transfer from symbolic reasoning to this domain. How do you leverage testing information in order to strengthen the verification, or use the verification to improve the adversarial attack generation methods? How do you battle the approximation loss downstream? This is a major problem. If you're looking at these things, this here, if you have, and you'll see this in many works, they usually talk about few layers. There is a reason for this. The deeper you go inside the network, the approximation loss piles up, and you may really start losing information here. This is a real problem. So how are you going to use refinement of some kind here? This has not been explored at all. That's as far as specification and verification, some of the issues. Now for networks, what people have looked at, is mostly classification, but classification is a small part of deep learning. It's one of the parts of deep learning. There is reinforcement learning, there is regression, there is a current neural networks, there is many other setups here. There is generative models combined with classification, followed in a pipeline. None of this really yet are addressed by these methods. End-to-end system of some kind. Finally, there are many interesting questions here that are of more fundamental nature, in the sense of more theoretical nature, let's say. Is one thing that you observe is when you make your network more provable, the accuracy tends to go down. The accuracy tends to go down. You are getting more provable, but you are less accurate. Okay? So it could be the case that you just cannot make your network that robust, no matter what you do, because the topology you picked is of a particular kind. And so this trade-off here of accuracy of prediction versus how provable your network is, this is almost not yet looked at much. Okay. So there is a whole space here where I think, at least in our experience, there is so much work that can be brought from the symbolic community into this space that it's not yet there at all. So this is really what I wanted to talk about the open problems and what we're looking at right now. And that's it.
Thank you. Yeah.
So in your slide on transferring logic to loss, how do you know that the logical formula is going to lead to a convex solution? So if you want to apply gradient descent methods subsequently,
no, you don't know this.
Convex, yeah.
You don't know this.
You don't know it's convex,
what you do know is that if your translation is at 0, if you find the solution to the loss at 0, then that solution satisfies the formula, kind of what Zhendong was talking about.
Right, but in the absence of that, there's no sort of other, there's no sort of structure on the logical formula that can relate it to a convex solution, right?
I mean, you can restrict it to be like a convex polyhedra or something.
Okay.
And then you can get more convex problems, yes. I don't know where to stop, but okay, I'll stop here.
Awesome topic. I love it. Just a question about the confidence interval. You mentioned it quickly at the beginning. How do you model a confidence interval as part of the result for checking against adversarial attacks?
So let's see which one. There is like this one here, or you're talking about this one?
There was a 0.095 confidence interval at some point.
Why? Where is it? God knows. Let's see. There are not many slides.
No,
I don't know where it is, but I'm not sure which confidence interval.
it's here.
This one?
You find that it's a track or it's a...
This you can look at the softmax at the end of the final layer. It gives you this probability on the labels. It says this label has this probability and this label has this probability.
Okay.
So that's what it is. Yeah, this is easy. Yeah. I have questions.
Yeah, so these LP norm specifications.
Go there now. Yes.
Actually, the slide you're on is a good one for my question. The one with the stop sign and everything on it.
Yes.
Like these LP norm specs don't really seem to address physical world attacks at all. And I was wondering if you thought about how symbolic or formal methods could possibly inform something like this, where the attack is sort of getting at something essential about the hypothesis space and the problem and things that we don't really know about until we've done the learning.
Yeah, so what you're saying is that a lot of the noise, like norm-based noises that people add, are not really, let's call them real-worthy enough, right? So one of the attacks is, that we looked at recently, and that's in the Popper paper, is geometric perturbations like rotation. So you can take it and rotate. That's kind of physically feasible. And there we can show for the first time that you can actually prove, let's say, that the rotation between minus 45 degrees, minus 25 degrees to 35 degrees, anything in the ranges is the same. Now the question is, to do this, you cannot capture the space of attacks in a box. It is not a box. So what you have to do there is to, at least what we did, but you can do better than that, is you can take the code that takes an image and takes the angle and analyze that with abstract interpretation to compute a summary and feed that through the network. You're not going to capture many of these attacks with boxes or things like this. Yeah. But that I think the specs are we have to work more on specs, I think, before verification even.
Any other questions? Yeah.
Could you go to the next slide?
Next slide.
Yeah, the abstract interpretation one.
Oh, yeah, okay.
Yeah, this one. My question is, so first thing is, why not symbolize the array input, like x0, x2?
So this thing here is a brightening attack. Here you take only some of the pixels and you make them symbolic. You can, if you have an L infinity attack, like L infinity norm, here you symbolize everything. Everything becomes like epsilon 1, epsilon 2, epsilon 3 within some range. So everything gets symbolized. Depends on the attack, different. So L infinity, yes, everything would get symbolized here.
Okay.
You'd get 784 epsilons.
I see. Yeah, I'm just trying to understand whether there are some like scalability.
Yeah, for sure. Like, if you don't, so the fewer epsilons you have, the easier it is to analyze. Brightening attacks are much easier to analyze than L infinity attacks. Exactly because of your point, because there is much fewer epsilons to start with. I only pick few pixels to brighten, not like the whole thing. Yeah. Yeah, Zhendong.
So just to follow up on this question, right? I guess you can take an image and try to infer what are the critical pixels, right? In the sense, for the critical pixels, maybe your deltas should be smaller, but for the other ones, like you can allow bigger epsilons, right? In the sense that you'll be able to verify it, the properties will be stronger.
Yes. So what you're saying in a sense is that the epsilon is not uniform. Yes. It's a good point. You can try epsilons and try to infer epsilons, which is like some pixels are less important than others. Yes, some pixels you can perturb a lot. If I have a stop sign and I put a dot here and I make it can range probably between anything and anything, right? So, yeah.
Okay, so let's take the rest of the discussion offline and thank Martin again.